So there's a whole bunch of information crammed into 7.4. The first thing we want to start with is separation of variables. So this actually, a lot of times we'll be dealing with the slope fields. And so think about if we start with dy dx equals a function in terms of y times a function in terms of x. We want to separate the variables. So I'm going to multiply both sides by dx, putting the x's on the right side. Then I divide by f of y. And I kind of like to write it this way because it keeps the function of y separate from the dy. And what this allows us is, then we'll move into, we can integrate this side in terms of y, and we can integrate this side in terms of x. That's the big idea with separation of variables. And I can guarantee you, you're going to see quite a few problems on the AP test with this. Okay, so the first thing we're going to do, first of all, I'm going to rewrite this. And I'm going to actually write this as x squared times y squared, just to get them in separate pieces. So you're either going to multiply or divide to move things from side to side. You cannot add or subtract with separation of variables. It has to be multiply or divide. So I'm always going to put the dx by multiplying both sides. This time, since x squared is being multiplied times y squared, I'm going to divide both sides by y squared. So let's rewrite this so it looks a little bit nicer. And then, so we're solving for y. This is our initial value. We want to get y by itself. We want to have y equals what original equation. So then we integrate both sides. Now, when I integrate 1 over y squared, remember we have to move this up. So really what we're integrating is y to the negative 2. I'll just bring this side down. So if I add 1 and divide, that's y to the negative 1 divided by 1. Now, we don't need a plus c for both sides. You technically would have a constant on the left, a constant on the right, and then you could combine them to get a constant. So we always just put the plus c at the end of the right side on the x side. Then we add 1 and divide, and the plus c just goes on the very far side. Okay, now we have to get y by itself. This is kind of a hot mess. So let's think about what this y is saying. I'm going to move this back down. So if I'm dividing by negative 1, it makes the fraction negative. I'm just going to put a 1 over y to the first on the bottom. So that just makes this part a little bit nicer. Okay, so at this point, we can solve for c, because they give us x and y. So we can substitute our x and y in for 1 and 1 in for x and y. So I'm going to kind of come back up here. So if I plug 1 in for y, I get negative 1 here equals 1 to the third divided by 3. So I get negative 1 plus equals 1/3 plus c. So I'm going to subtract and get negative 1 1/3 for my c. Now, when I plug that back in, I'm going to write this mixed number as an improper fraction. It's going to make life a little easier. Okay, so if I want to get y by itself, I need to get y out of the denominator. So what I'm going to do First of all, I'm going to make this side one fraction. I'm going to get a common denominator, which is 3, and then I can just put it. And at this point, there's a couple of ways you can think about it. I can multiply by y. I have to get y out of the denominator. So I'm going to put multiply by y. You could think of it as cross, multiply, and divide to get y by itself. Probably the better way is to move the y up to the other side, then multiply by the reciprocal of this. So, and I got this negative here, so I get negative 3, and I get y by itself. So the better, if you have y in the denominator, it's helpful to have this side all in one fraction because you can just multiply by this reciprocal and move it to the other side. And this is my final answer because we have y by itself. Okay, so this is like the most generic law of exponential change. And this is how we develop, if you think about PERT, this is where PERT comes from. It didn't just like magically appear. It actually comes from this particular, deriving this formula into PERT. So this is kind of slick. So we set our derivative of y with respect to t equal to some constant times y. All right, this is how all of these start. Now we're going to do our separation of variables. So you recognize this. Anytime this b whatever variable matches a variable on the other side, that's when you need to switch things up. Now, I always leave the constant on the right side. So I'm going to get 1 over y dy equals constant dt. Now we're going to solve for y by separating the variables. That's what we just did. Then we can integrate both sides. Okay, on the previous problem, it was 1 over y squared. This one's 1 over y, antiderivative of 1 over y, ln. Very, very important. With separation of variables, we will see 1 over y a lot, so that's something you've got to really be careful about. And you will get better about. Equals, this is just a constant. So with all constants, you just put a t in next to the constant, plus c. Okay, so now what is it that we do if I want to cancel out ln to get y by itself? The inverse of ln is e. So I'm going to e both sides because e cancels out ln. And I get e to the kt plus c. All right, here's a sneaky little thing here. I'm going to come up here. So does it make sense that if this whole thing is together in the numerator, we could also write this as e to the kt times e to the c? Because if the bases are the same, you can add the exponents. I'm going backwards. I'm separating the exponents into 2 separate bases of e. And if my constant is just some constant, doesn't it make sense that e to a constant is also just a constant? They're different constants, but it's representing a constant. So I'm going to write this as a big capital C because this is e to the kt times some constant. Technically, if you remember your PERT, this is like your p, e to the rt. This is where PERT comes from. So it's kind of slick the way that works, but typically we just use a capital C in as a constant out in front. So sometimes you can solve it for it back here, but this is just easier to write as a final thing. So we're going to be doing word problems where we're developing this and ending up with an equation. So it's a little bit ugly, but okay. So this actually spells it out, but it doesn't say PERT. It just says, and I'm going to write this out. And I want you to think about always and forever. This is always representing the final amount of anything, whether it's money, whether it's grams of, like in exponent or in biology, you'll talk about exponential growth and decay. So this is always the final amount. Anything sub-zero, and recognize this is like our constant, this always represents the initial amount. Anything sub-zero is always the initial amount. The time is t. Now, depending on the word problem, it could be time in terms of years, it could be time in terms of days, and k is always the constant. Now, sometimes when we're talking about compounded interest, money, this only represents, if this is in terms of money, this represents continuously compounded. If E is involved, it's only continuous. Now, you might not have room, but if it's compound anything else other than the word continuous, just jot this down. You have used this formula in the past and it's a big pain in the butt. But say like N is the number of times per year. T is time in years. This one has to be in years. R is the rate. P is the principal or your initial amount. Okay. All right. Oh, yeah. I was thinking that wasn't included, but so this is just this is your continuous, this is everything else. Okay, so this is going to just compare continuous to quarterly. So A is the easiest. As soon as I see the word continuous, I think PERT. A equals initial amount is 800, E to the R, and remember, all decimals we need to move 2 places 4%, so that's 0.063, 8 years. So you literally just take 800 in your calculator times E raised to the 0.0638. Sometimes what I'll do just to make sure, just be kind of careful, make sure, I mean, you can just probably type it in just like that. But you should get, when you type all this in, and when dealing with money, I'm always going to round it to the nearest cent. And remember, you're going to find E, because it's the inverse of ln, it's just 800 times second ln, and then it kicks up the exponent that you can just put all of that into the exponent. All right, so B What B does basically is just rearranges E. It's not E any longer. It's kind of more complicated. Now, because it's quarterly, so let me just kind of write this out. Our principal initial amount is 800. N is the number of times per year. Quarterly means 4 times a year. T is 8. And R is the 0.063. So we just plug this into that complicated, ugly, yucky formula. And this is just the NT, which is 32. Okay, so with the graphing calculators, it's super nice that you can literally just type it in just like that. But I always say the calculators are also just as good as the operators, so it has to be entered in perfectly. But once again, I'm going to round that to the nearest cent. So you can see that continuous is just a few $5 more than quarterly. So not a huge difference, but just be really careful. So sometimes what I would do, if you struggle with this, is add this up first, and then you could take 800 times that amount, raised to the 32. But I always multiply the exponents together. I think that's helpful, because then you're just entering a number at the top. All right, so radioactive decay. So let's think about decay just means it's getting smaller. So since it is getting smaller, does it make sense my exponent will be negative? Okay. K is greater than 0, but it's a negative exponent. If it's decay, the exponent needs to be negative. So really just this particular formula is the big thing that you need. And understanding what half-life is the time required for half of it to decay. So sometimes I like to just kind of show some examples. Say that this, if we start out with an amount and we talk about half-life. So say we start out with 100. If the half-life is, I don't know, 8 years, I'll just make something up. After 8 years, you're down to 50. After 16 years, you're down to 25. After 24 years, you're down to 12.5. So the half-life is saying after this many years, it's decaying to this amount each time. So just that general understanding of what half-life means is kind of important. Okay, so it says find the half-life of a radioactive decay equation and show that it only depends on K. All right, so we're going to start with this general. The general equation. And what will Y equal after its half-life? Well, if this amount was 50, after its half-life, it would be half of that, right? So what I'm going to do is say in just any general, I'm going to start with Y will be half of the original amount. So whatever I started with, the final amount will be half of the original. So this part is kind of slick. If both sides are being multiplied by y sub 0, I can divide both sides by that initial amount, and the initial amount is no longer there. Now, at this point, we want to solve for t. So I have to get rid of e to get to t. So what's the inverse of e? Is ln. So I need to ln both sides. Then ln cancels out e. Then to solve for t, divide by negative k. Now I'm going to show you something kind of slick that's helpful to remember. I'm going to rewrite this ln of 1/2. And watch what I'm going to do. I'm going to bring the 2 to the top. So that makes my exponent negative. And think back to your log properties. If you have a power, you can bring that power to the front. So if I have -1 times ln, this negative cancels this negative, and ln2 divided by k is a whole lot nicer than ln 1/2 divided by negative k. And they're equivalent. So understanding how to get from here to here is good. So what this wanted us to show is that every time we do half-life, this is always going to be a half, that the time period is always going to be ln2 divided by the constant every single time. Oh, and that's what this the definition says. Half-life will always be ln2 divided by k. All right. For some reason, I just always skip this problem, so we're going to just skip it. Then we have 11. No, page 11, example 5. Okay. So it says scientists who use carbon-14 dating use 5,700 years for its half-life. All right. Find the age of a sample in which 10% of the original have decayed. Okay, all of these values are going to be important, and the terminology is very important. So when we think back to the whole why, this whole general equation is, and this is, we're going to do a little bit more with this, but remember, this is the amount, the final amount, the amount that's present in general. Now, in this particular problem, we're not going to use E though, because this is half-life. So we're going to kind of alter this just a little bit and kind of play with it. So I use this, I would say, for the majority of the word problems. But if it says half-life, the rate it's decaying is by 1/2. So watch what we're going to do. First of all, if we want to have 10% decayed, what's the percent that is present? If there's 10% decay, that means there's 90% left. So we want to think about that. Because this is our final amount, the amount that's left, I'm going to put 0.9 on this side because that's how much will be present when we get done. All right, so this whole side, we just start with 1/2 because we kind of think of it as, if we're talking in terms of percent here, it's like we're starting with a whole. This is one whole, and I'm going to be left with 90% of this one whole. Then we have the rate it's decaying at, and then our time. What we end up doing with half-life is always dividing by the half-life years, because it's only going to take half of it every 5,700 years. So after 5,700 years, that's one half-life period. So you always take the time divided by the half-life. All right, now I'm going to solve for t to find the half-life, because we're looking for the age, the time period. So in order to get to t, I'm going to ln both sides, because that's 1, I don't need to worry about it. So I get, let me write this all out. ln 0.9. Now, the whole point of getting to this up here, I'm going to scoot this over, because what do I do with the exponent? The whole point of taking the log on the right side is so I can move this in front of the log. So it looks like this. Okay. So then I'm going to solve for t, I need to multiply by 5,700. I need to divide by ln 1/2. So this gets to be a little bit of a logistical nightmare, but plugging all of this in, I'm going to round this to the nearest year. So plugging all of this into your calculator should be approximately 866 years. So if you think about this, it says it takes 5,700 years to get to half of it. Does it make sense if we only get to, if we're losing 10%, it only takes 866 years. So if you get some weird wacko number, it needs to be less than the half-life. Okay? Okay, last big topic is Newton's law of cooling. Now, Newton's law of cooling, I know in physics sometimes people have dealt with this formula and they've seen an easier formula, they've seen a lot of different variations. This is your general Newton's law of cooling, like your starting point. So we're looking at the actual one. Okay, so this whole great big mess, I'm going to do this. So this is the formula, and let me do this so you're able to see it better. So it's T minus T sub S equals the quantity T sub 0 minus T sub S times e to the negative kt. All right, so the first thing you need to know, T is the final temperature. So think about like if you pull a pizza out of the oven, this would measure after so many minutes what's the actual temperature of the pizza. So this is your final temp. T sub S is the surrounding, S for surrounding temperature. So if you pull that pizza out, what's the temperature in your kitchen? T sub 0. What's always sub 0? The initial. And then the little t, notice that a lot of these are capital. The little t here is time. So it's really not a, it's kind of complicated, but it's really not once you kind of get the feel for it. But the name of it is Newton's law of cooling because Isaac Newton. All right, so last example. All right, a hard-boiled egg at 98 degrees. So that's our initial temp. Is put into a pan under running 18 degrees Celsius. So that's your surrounding temperature. The egg is surrounded by 18. after 5 minutes, now we have to be careful. This is a couple of problems. This 5 minutes is going to allow us to figure out what our constant is, because this says how much longer, so I want to caution you here. The egg's temperature after 5 minutes is 38. So this kind of all goes together. So we're going to plug all of this in, and this is going to allow us to solve for K. So I know there's like not much room, but I kind of squished this all into one side, and then we'll figure out the next part. Okay, so we've got let me just rewrite T minus surrounding temperature equals initial minus surrounding e to the negative kt. All right, so capital T, 38 minus T sub 0, or T sub s, equals T sub 0 minus T sub s e to the negative 5k. So see how we can plug all of this in, and we are left with one variable. This allows us to solve for that constant. So 38 minus 18 is 20. 98 minus 18, 80. Okay, so another little logarithm concept. You cannot take a log until the e is by itself on this side. So the first thing we're going to do, divide by 80 so I can get e by itself, because to solve for k. So this is 1/4. I'm going to ln both sides, because that cancels this out. And then to solve for k, I divide by -5. Now, if you remember that little trick from before, I can move this up. That'll be ln 4 to the -1 divided by -5, then the negatives cancel. This is a much easier k to deal with. Now it wants to know how much longer. So if it's down to 38 degrees Celsius after 5 minutes, how much more will it take to reach 20? All right, so now 20 is the new final T. So I'm going to make my final temperature to be 20. My surrounding temperature is still the same, of 18. And my initial temp, so we take our initial minus the surrounding. That's still our 80 minus our e to the, all right, ln 4/5 t. Now, be careful, because this needs to be a negative to make it decay. So the constant's ln 4 divided by 5. We just have to make that whole thing negative. Okay, so I'm going to subtract this. And we can divide. ln, and for some reason I don't have this finished. So I just cheated. So I didn't have this written out in my book. We should get 13.3 minutes. But be careful. This was the total amount of time it took to get down to 20. Remember, we started with it 5 minutes. It was down to 38. It said how much longer. So I'm going to say after 8 more minutes, because my 8 plus 5 gives me the 13. So this part here, you've got to really read the directions and understand what it is it's looking for. And that is section 7.4.